Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting far beyond our world into the vast and astonishing expanse of outer space. Above you, beyond the sky you see each day, lies a universe so immense that even light takes billions of years to cross it. It is a place where stars are born in darkness, where entire galaxies move in slow, silent collisions, and where time itself can stretch and bend in ways that seem almost impossible. Out there are worlds of fire and ice, wandering planets with no sun, and forces so powerful they can reshape the very fabric of reality. As we travel through this boundless cosmos, you may find yourself seeing familiar things in a new way. The night sky, the stars, even your own place within it all, may begin to feel deeper, stranger, and far more connected than you ever imagined. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften. Let your breathing slow, and allow your mind to settle into stillness as we explore the vast universe together. Let's begin. The universe began with space itself, suddenly stretching into existence. This was not an explosion inside an empty room. There was no outside darkness waiting for matter to rush into. Instead, the room itself began to grow. Space expanded from an unimaginably hot and dense state, carrying energy, light, and the seeds of everything with it. In its earliest moments, the universe was far too extreme for atoms, stars, planets, or even ordinary light to exist as we know them. It was a rushing sea of particles and radiation, changing faster than the mind can easily picture. As it expanded, it cooled. Tiny differences in density began to matter. Those faint, uneven patches would later become galaxies, stars, and worlds. So when we talk about the beginning of the cosmos, we are really talking about the birth of distance, time, structure, and possibility itself. Every atom in your body was forged inside ancient stars. The calcium in your bones, the iron in your blood, and the oxygen you breathe were not made on Earth. They were created through cosmic processes long before the planet existed. Lighter elements formed in the early universe, but many heavier ones required the crushing furnaces inside stars. Deep in stellar cores, atoms fused together under immense heat and pressure. When massive stars reached the end of their lives, they exploded and scattered those ingredients into space. Later, that enriched material gathered into new stars, planets, oceans, rocks, and eventually living things. You are not separate from the universe looking up at it from below. You are made from its older chapters. Every heartbeat depends on matter that once burned in distant suns, then drifted through space before becoming part of a living body. Looking into space means looking backward through time. Light does not arrive instantly. Even at its incredible speed, it still needs time to cross the distances between worlds, stars, and galaxies. The moon appears as it was just over 1 second ago. The sun appears as it was more than 8 minutes ago. A star that sits hundreds of light years away is showing you a version of itself from centuries in the past. With powerful telescopes, astronomers can look so far across space that they see galaxies as they were billions of years ago, when the universe was younger and more crowded with newborn stars. This makes astronomy unlike almost any other science. The sky is not only a place, it is a record. Every distant point of light is a message that left long before it reached your eyes. Black holes can slow time almost to a standstill. Near a black hole, gravity becomes so intense that it changes the flow of time itself. This is not a trick of perception. It is a real effect predicted by relativity and confirmed in gentler forms near Earth. The closer an object gets to a strong gravitational field, the slower its clock runs compared with clocks farther away. Around a black hole, this difference can become extreme. To a distant observer, something falling toward the edge may seem to fade and freeze as its light stretches and dims. For the falling object itself, time continues normally. This strange split shows that time is not a universal rhythm shared everywhere at once. It can bend with gravity, stretch with motion, and behave differently depending on where you are in the universe. Most of the universe is made of something we cannot see. Everything familiar, including stars, planets, gas, dust, people, and light itself, appears to make up only a small fraction of the cosmos. The rest is dominated by two mysteries. One is dark matter, which does not shine, absorb light, or reflect it in any ordinary way. We know it is there because galaxies rotate, as if held together by far more mass than we can see. It also bends the light from distant objects through gravity. The other mystery is dark energy, which seems connected to the accelerating expansion of space. Together, these hidden components shape the universe on the largest scales. It is a humbling thought. Nearly everything we study directly is only the visible edge of a much deeper reality, moving silently behind the scenes. There may be more stars than grains of sand on Earth. The number is almost too large to feel real. Our own galaxy holds hundreds of billions of stars, and the observable universe contains billions or even trillions of galaxies. Some are grand spirals. Some are faint dwarfs. Some are ancient swarms of red and golden light. When astronomers estimate all those stars together, the total rises beyond ordinary imagination. It may exceed every grain of sand on every beach and desert across our planet. Yet each star is not just a point. It is a sun with its own history, chemistry, temperature, and possible family of planets. Some will live briefly and die in spectacular explosions. Others will glow steadily for trillions of years. The night sky can look sparse from Earth, but in truth, we are gazing into an ocean of suns. Some planets wander forever without any star to warm them. Not every world belongs to a solar system. Some planets drift alone through interstellar space, untethered from any sun. They may have formed around stars and later been thrown away by gravitational encounters with larger planets or passing stars. Others may have formed directly from collapsing clouds of gas and dust, more like tiny failed stars than ordinary planets. Without sunlight, their surfaces would be unimaginably cold. Yet some might keep internal heat from their formation, radioactive decay, or thick insulating atmospheres. A few could even hide buried oceans beneath crusts of ice. These rogue planets remind us that space is not only filled with orderly systems and circling worlds. It also contains lost wanderers, moving through the dark between stars, carrying their own sealed histories into the endless night. The Milky Way is already colliding with another galaxy. Our galaxy may seem calm from inside, but it is surrounded by smaller companions being stretched and absorbed by gravity. One of them, the Sagittarius dwarf galaxy, is already being torn apart as it passes through and around the Milky Way. Its stars are not crashing into ours like sparks from a fire. Space is far too empty for that to happen often. Instead, the collision is slow, vast, and ghostly. Streams of stolen stars arc around our galaxy like faint trails left behind by an ancient visitor. These encounters help build the Milky Way over time. They add stars, stir gas, and reshape structure across billions of years. Our home galaxy is not finished. It is still feeding, growing, and changing through mergers that unfold almost too slowly for human history to notice. The Moon is slowly drifting farther away from Earth. Each year, the Moon moves a little farther from us, about the width of a few fingernails. The cause is hidden in the tides. As Earth rotates, ocean water is pulled by the Moon's gravity, creating tidal bulges that do not line up perfectly beneath it. Because Earth spins faster than the Moon orbits, those bulges tug the Moon forward. That tiny gravitational pull gives the Moon energy and gradually pushes it outward. At the same time, Earth's rotation slows by a small amount. Long ago, the Moon was much closer, and tides were stronger. Far in the future, it will appear smaller in the sky. This slow separation is a reminder that even the most familiar relationship in the night sky is changing, measured not in drama, but in patience. Space is not empty. It hums with invisible fields and particles. Between planets and stars, there is no air to carry sound as we know it, but that does not mean nothing is there. Space contains thin gas, drifting dust, magnetic fields, radiation, and streams of charged particles from stars. Even regions that seem vacant can hold faint traces of matter spread across enormous distances. Quantum physics adds an even stranger layer. What we call empty space is filled with fields that can fluctuate, interact, and give rise to particles under the right conditions. Around Earth, invisible magnetic shields guide solar particles into auroras. Between galaxies, tenuous material stretches through the cosmic web. The emptiness of space is not a simple void. It is a restless stage where forces pass, light travels, particles drift, and the universe quietly continues its work. The Sun loses millions of tons of mass every second. The Sun looks steady from Earth, yet it is constantly transforming itself into light. In its core, hydrogen atoms fuse into helium under crushing pressure and enormous heat. A tiny amount of mass is lost in every fusion reaction, and that missing mass becomes energy. It streams outward through the star, slowly works its way to the surface, then flies into space as sunlight. By the time it reaches Earth, it warms oceans, drives weather, feeds plants, and makes almost every familiar form of life possible. The scale is astonishing. Every second, the Sun converts millions of tons of its own substance into energy, and still, it has enough fuel to shine for billions more years. Its brilliance is not a surface flame. It is matter becoming light in the heart of a star. Jupiter is so massive, it almost became a star. Jupiter is often called a planet, but it is also a giant world that hints at something larger. It contains more mass than all the other planets combined, and its gravity is strong enough to shape much of the solar system. Yet it never gained enough material to ignite the nuclear fusion that powers true stars. Deep inside, pressure squeezes hydrogen into strange forms, including metallic hydrogen, which can conduct electricity and help generate Jupiter's enormous magnetic field. The planet gives off more heat than it receives from the Sun, a leftover warmth from its formation and slow contraction. If the early solar system had provided far more gas, Jupiter might have become something like a small star. Instead, it remained a colossal planet, guarding moons, storms, and mysteries beneath its banded clouds. Saturn's rings are thinner than most people imagine. From a telescope, Saturn looks grand and jeweled, with rings wide enough to span an enormous distance around the planet. Yet their thickness is surprisingly small compared with their width. In many places, the ring system is only tens of feet to perhaps a few stories thick. It is made from countless icy particles, ranging from tiny grains to chunks as large as boulders, all orbiting Saturn in a delicate, flattened disk. The rings are not solid, and they are not perfectly permanent. Gravity from nearby moons shapes gaps, waves, and ripples through them. Over time, ring material slowly falls into Saturn as a kind of icy rain. What seems eternal may actually be temporary on cosmic scales, a magnificent feature we are lucky enough to see while it still shines. Venus has a day longer than its year. On Venus, time behaves in a way that feels almost upside down. The planet rotates so slowly that one full turn on its axis takes longer than its entire trip around the Sun. Even stranger, it spins in the opposite direction from most planets, so the Sun would rise in the west and set in the east beneath its thick clouds. The surface is hidden under a crushing atmosphere rich in carbon dioxide, where pressure is intense and temperatures are hot enough to melt lead. Its slow rotation may have been shaped by ancient collisions, tidal forces, or the drag of its dense air. Venus is nearly Earth's size, yet its rhythm is utterly alien. It shows how two neighboring worlds can begin with similarities and end as profoundly different places. Mercury has ice hiding in permanent shadow near its poles. Mercury is the closest planet to the Sun, so ice sounds impossible there. Its dayside can bake under extreme heat, yet near the poles, deep crater floors never receive direct sunlight. Because Mercury has almost no atmosphere to spread heat around, those shadowed places remain intensely cold. Over long stretches of time, water molecules delivered by comets, asteroids, or internal processes may have migrated into these dark traps and frozen there. Radar observations and spacecraft measurements have revealed bright deposits consistent with water ice. This makes Mercury a world of sharp contrasts. One landscape can be scorched by sunlight, while nearby shadows preserve frozen material for ages. The discovery reminds us that planets are not defined by simple labels. Even a seemingly burnt world can keep cold secrets in places the Sun never reaches. Mars once had rivers, lakes, and possibly a northern ocean. Today, Mars is cold, dry, and dusty, but its surface still carries the traces of a wetter past. Spacecraft have photographed branching valleys, dried lake beds, river deltas, and minerals that usually form in the presence of water. Some ancient regions look as though streams once flowed across them for long periods. Other evidence suggests that a large body of water may have covered parts of the northern lowlands, although scientists still debate the details. The planet lost much of its atmosphere over time, which made stable surface water difficult to maintain. But the old terrain remains like a fossilized memory. Mars was not always the desert we see now. It may once have had shorelines, storms, and moving water beneath a thicker sky, making it one of the most compelling worlds in the search for ancient habitability. Uranus spins sideways, as if something knocked it over. Most planets rotate with their poles roughly upright, compared with their paths around the Sun. Uranus is different. Its axis is tilted so dramatically that it rolls around the Sun almost on its side. This gives the planet extreme seasons, with each pole spending decades pointed toward or away from the Sun. One leading idea is that a massive impact early in its history knocked Uranus into this strange position. Another possibility involves complex gravitational interactions with other bodies before the solar system settled into its present form. Whatever happened, it left behind a world with pale blue clouds, faint rings, and moons that follow its tilted orientation. Uranus is not just another distant ice giant. It is a clue to the violent early history of planetary formation, when collisions could rewrite the fate of entire worlds. Neptune has winds faster than the speed of sound. Neptune receives only a tiny fraction of the sunlight that warms Earth, Yet its atmosphere is astonishingly active. Clouds race through blue skies at speeds that can exceed the speed of sound on Earth. These winds are among the fastest measured anywhere in the solar system. The energy behind them is still not fully understood, but Neptune radiates more internal heat than it receives from the Sun, and that heat may help stir its atmosphere. Methane in the upper air absorbs red light, giving the planet its deep blue color. Dark storms can form and vanish, some large enough to be seen by passing spacecraft and powerful telescopes. At the edge of the planetary realm, where sunlight is weak and cold dominates, Neptune refuses to be still. It is distant, frozen, and violently alive with weather. Pluto has mountains made of water ice. When New Horizons flew past Pluto, it revealed a world far more complex than a simple frozen rock. The surface showed bright plains, dark regions, hazes, glaciers, and rugged mountains. Some of those mountains are made of water ice, which behaves like hard bedrock in Pluto's extreme cold. On Earth, water ice can melt in your hand. On Pluto, it can stand as a mountain range. Softer ices, such as nitrogen ice, flow more like glaciers across broad plains. One famous heart-shaped region contains a smooth basin that appears geologically young, with cells of slowly churning ice. This distant dwarf planet surprised nearly everyone. Instead of being dead and plain, it is layered, active, and strange. Pluto proved that even small worlds at the edge of sunlight can hold landscapes of breathtaking complexity. Titan has rivers and lakes filled with liquid methane. Saturn's largest moon has a thick atmosphere, orange haze, weather, dunes, river channels, and lakes. But its cycle is not based on water at the surface. Titan is so cold that methane and ethane can exist as liquids. They fall as rain, carve channels, gather in lakes, and evaporate back into the sky. From above, some polar regions look almost familiar, with shorelines and dark liquid bodies spread across the landscape. Beneath its icy crust, Titan may also hide an ocean of liquid water mixed with other compounds. This makes it one of the most intriguing places in the solar system. It has Earth-like processes using alien materials. On Titan, chemistry writes a different version of weather, where the rivers are hydrocarbons and the rocks are water ice. Europa may hide a salty ocean beneath its frozen shell. Jupiter's moon, Europa, looks like a cracked white sphere crossed by reddish-brown lines. Beneath that frozen exterior, many scientists think there is a global ocean of liquid water. Tidal forces from Jupiter and nearby moons flex Europa as it orbits, creating internal heat that may help keep water from freezing completely. The surface cracks and shifting ice patterns suggest movement from below. If the ocean touches a rocky seafloor, chemical reactions there could provide energy sources, much as they do around deep-sea vents on Earth. That possibility makes Europa one of the most exciting places to investigate for habitability. It is not appealing because it resembles Earth on the outside. It is compelling because, under its ice, it may hold one of the essential ingredients for life in vast and hidden abundance. Enceladus sprays ocean water directly into space. Saturn's small moon Enceladus stunned scientists when spacecraft saw plumes erupting from fractures near its south pole. These geysers release water vapor, ice grains, salts, and organic molecules from beneath the surface. The material sprays outward into space, feeding one of Saturn's faint rings and offering a direct sample of the moon's interior without needing to drill through ice. Evidence points to a subsurface ocean in contact with a rocky core. That contact matters because rock and water can exchange chemistry, creating conditions that may support complex reactions. Enceladus is small, bright, and frozen from the outside, but beneath its crust it may be warm enough for liquid water to persist. Few worlds feel so secretive and generous at the same time. It hides an ocean, then sends pieces of it into the sky. Io is the most volcanically active world we know. Jupiter's moon Io is constantly pulled and squeezed by gravity. Jupiter tugs it one way, while nearby moons help keep its orbit slightly stretched. This repeated flexing generates intense internal heat, and the result is a surface covered with volcanoes, lava flows, and sulfur-rich deposits. Some eruptions launch material hundreds of miles above the moon. Unlike Earth's volcanism, which is driven largely by internal heat and plate tectonics, Io's activity is powered by tidal forces. Its surface changes quickly, with new deposits covering older terrain. The colors can look yellow, orange, white, and black because sulfur and volcanic compounds paint the landscape. Io shows that a moon does not need to be large to be geologically fierce. In the grip of a giant planet, it becomes a restless volcanic world. Ganymede is larger than the planet Mercury. Ganymede is a moon, but its size belongs in planetary conversation. It is the largest moon in the solar system, bigger than Mercury and only slightly smaller than Mars. Orbiting Jupiter, it has a surface of ice and rock marked by bright grooves, darker ancient terrain, and impact scars. Even more remarkable, Ganymede has its own magnetic field, something no other known moon can claim in the same way. Beneath its crust, there may be layers of liquid water sandwiched between different forms of ice. Its interior is differentiated, meaning heavier materials sank inward, while lighter ones rose outward during its history. Ganymede is not simply a satellite circling a larger body. It is a complex world in its own right, with geology, magnetism, and possible hidden oceans woven into its story. Triton orbits Neptune backward, unlike most large moons. Triton moves around Neptune in the opposite direction to the planet's rotation. That unusual backward orbit strongly suggests it did not form there. Instead, Triton was probably captured from the outer solar system, perhaps from a population of icy bodies beyond Neptune. Capture would have been a dramatic event, likely disturbing or destroying earlier moons as Triton settled into its new path. Today, it is a cold world with a thin nitrogen atmosphere and geyser-like eruptions that may send dark material across its surface. Its orbit is slowly changing, and far in the future it may move close enough for Neptune's gravity to tear it apart, possibly forming rings. Triton feels like an adopted world with a turbulent past. It carries the chemistry of distant origins while circling a planet that claimed it by force. The asteroid belt is mostly empty space between scattered rocks. Science fiction often shows asteroid fields as crowded obstacle courses, but the real asteroid belt is enormously spread out. It lies between Mars and Jupiter, and although it contains millions of objects, the distances between them are usually vast. A spacecraft can pass through without needing to dodge rocks at every moment. The belt likely contains leftover building blocks from the early solar system that never formed a planet, partly because Jupiter's gravity stirred the region too strongly. Its objects vary from tiny fragments to large bodies like Vesta and Ceres. Some are rocky, some are metallic. Some contain carbon-rich material that may preserve ancient chemistry. The belt is not a failed planet in any simple sense. It is more like a preserved construction yard, holding clues from the time when worlds were still being assembled. Ceres may contain more water than many icy worlds. Ceres is the largest object in the asteroid belt, and it is unusual enough to be classified as a dwarf planet. Spacecraft observations revealed bright salt deposits, clay minerals, and evidence that water played an important role in its history. Beneath its surface, Ceres may contain a mixture of rock, ice, salts, and possibly briny liquid pockets that survived longer than expected. Some bright regions appear to have formed when salty material rose from below and left reflective deposits behind. This makes Ceres far more interesting than a simple asteroid. It sits in the rocky inner solar system, yet it carries signs of water-rich chemistry more often associated with colder places. In a region between Mars and Jupiter, Ceres quietly preserves a record of how water and minerals moved through the young solar system. Comets preserve ancient material from the solar system's birth. Comets are often described as dirty snowballs, but they are more like frozen archives. They formed in the early solar system from ice, dust, and organic compounds that remained far from the sun's strongest heat. Many spent billions of years in deep cold, barely changed since the time planets were taking shape. When a comet swings close to the sun, its ice is warm and turned directly into gas, carrying dust outward to form a glowing coma and tail. That spectacular display is only the surface of their importance. Inside, comets preserve chemistry from the solar system's beginning. Space missions that have visited or sampled them reveal complex molecules, ancient grains, and clues about how water and carbon-rich materials may have traveled between worlds. A comet is a traveler, but also a time capsule. Halley's Comet has been watched by humans for centuries. Few objects connect astronomy and human history as beautifully as Halley's Comet. It returns to the inner solar system roughly every 76 years, which means many generations have seen it and wondered what it meant. Ancient observers recorded its appearances long before anyone understood its orbit. For some cultures, comets were omens. For modern science, Halley became proof that these strange visitors followed predictable paths around the sun. Edmund Halley studied earlier sightings and realized they were likely the same object returning again and again. When it reappeared as predicted, it transformed a mysterious sky event into a triumph of celestial mechanics. The comet last visited in the late 20th century and will return in the 21st. Each appearance links people across time, all watching the same icy body sweep back from the outer dark. Meteor showers happen when Earth crosses old comet trails. A meteor shower can feel spontaneous, as if the sky has decided to scatter sparks. In reality, many showers happen when Earth passes through streams of dust left behind by comets. As those tiny grains enter our atmosphere, they burn up high above the ground and create bright streaks of light. Most are no larger than pebbles or sand grains, yet their speed makes them glow dramatically. Because Earth crosses the same debris paths at predictable times each year, some meteor showers return like seasonal sky events. The Perseids, the Leonids, and others all connect us to trails of ancient comet material. Each streak is not a falling star. It is a tiny fragment of cosmic history, briefly visible as our planet sweeps through a dusty path around the sun. The International Space Station circles Earth every 90 minutes. High above the planet, the station is not floating still. It is falling around Earth so fast that it keeps missing the ground. Each orbit carries it across oceans, deserts, cities, storms, and night sides lit by rivers of human light. In one day, astronauts aboard it can see 16 sunrises and 16 sunsets. That means their bodies live inside a rhythm unlike anything on the surface, where morning and evening arrive again and again before the mind can settle. The station travels at roughly 17,000 miles per hour, yet inside, crew members drift through modules, conduct experiments, repair equipment, and sleep strapped gently in place. It is a laboratory, a home, and a lookout post all at once. From there, Earth becomes a moving world without borders, turning beneath them in blue and white silence. Astronauts grow taller in orbit, because their spines relax. On Earth, gravity is always pressing gently through the body. It compresses the spine throughout the day, which is why people can be slightly taller in the morning than at night. In orbit, that constant downward pull almost disappears. The discs between the vertebrae expand, and the spine lengthens. Some astronauts gain a little height while living in microgravity, although it fades after they return home. This sounds amusing at first, but it is part of the much larger story. The human body evolved for weight, pressure, and resistance. Without those familiar forces, muscles weaken, bones lose density, fluids shift toward the head, and balance systems become confused. Spaceflight reveals how deeply gravity is written into us. Even the shape of the body quietly changes when Earth's pull is no longer holding it in its usual form. Spacesuits are tiny spacecraft built around human bodies. A suit used outside a spacecraft is far more than clothing. It must create a survivable world in a place with no breathable air, no normal pressure, and extreme temperature swings. Inside, it provides oxygen, removes carbon dioxide, regulates heat, holds pressure around the body, and protects against tiny, high-speed particles. Gloves must be flexible enough for tools, but strong enough to survive the vacuum. The helmet gives visibility while shielding the face from harsh sunlight. Every joint has to allow movement without leaking the atmosphere within. When an astronaut steps outside, the suit becomes a personal life support system, shaped like a person but working like a vehicle. It is engineering wrapped around biology. For a few hours, a human can leave the shelter of a station or capsule and carry a small piece of Earth into space. Rockets work by throwing mass backward with enormous force. A rocket does not push against the air, which is why it can keep moving in the vacuum of space. It moves because of momentum. When hot gas blasts out of the engine in one direction, the rocket is pushed in the other. This is the same principle you feel when a balloon shoots across a room after you let it go. The difference is scale. Rocket engines burn fuel and oxidizer to create a fierce, directed exhaust moving at tremendous speed. The vehicle must carry nearly everything it needs, including the oxygen required for combustion. That is why rockets are mostly propellant at launch. They are built around the brutal math of escape. To rise from Earth, they must fight gravity, air resistance, and their own weight, all by hurling fire downward. The first footprint on the Moon may last millions of years. On Earth, footprints vanish quickly. Wind scatters them, rain softens them, plants grow through them, and rivers erase them grain by grain. The Moon has no weather like that. There is no rain, no flowing air, and no living surface to cover a mark. When astronauts stepped onto the lunar soil, their boots pressed patterns into fine, dusty material, created by countless impacts over billions of years. Those prints remain exposed to space, slowly altered only by micrometeorites, radiation, and the faint effects of the solar wind. They will not last forever, but they may endure for immense stretches of time. A single human step became part of the Moon's surface history. Long after the voices of that mission faded from radio, the marks stayed behind, fragile-looking yet strangely permanent under the black lunar sky. Lunar dust smells like burnt gunpowder to returning astronauts. The Moon itself has no air to carry scent, so astronauts could not smell the surface while standing outside. The surprise came after they returned to the lunar module. Fine dust clung to suits, gloves, boots, and equipment, then entered the cabin with them. Once exposed to oxygen and moisture inside, it gave off a sharp smell that several astronauts compared to spent gunpowder. The dust was also clingy and troublesome. It was made by endless impacts smashing rock into jagged grains, not by water and weather smoothing particles as on Earth. Those tiny shards could scratch surfaces, irritate lungs, and work their way into seals and mechanisms. The smell was a human detail from an alien place. It turned a world of silent craters into something strangely immediate, as if the moon had followed them inside. Earth's atmosphere glows faintly when seen from space. From orbit, the planet has a thin, luminous edge called airglow. It is not the same as city light, lightning, or auroras. It comes from atoms and molecules high in the atmosphere absorbing sunlight during the day, then releasing energy as faint light. To astronauts, this glow can appear as delicate bands of green, red, or golden color tracing the curve of Earth. It reveals something easy to forget from the ground. The atmosphere is not a thick shield extending forever upward. It is a slender layer wrapped around the planet, thin compared with Earth's size, yet vital to everything alive below. That faint glow marks the boundary between breathable home and open space. It is beautiful because it is real, but also because it shows how fragile our world's protective skin truly is. Auroras happen when solar particles stir Earth's magnetic field. The sun constantly releases charged particles into space. Most would be dangerous if they reached the surface directly, but Earth's magnetic field guides many of them toward the polar regions. There, they collide with atoms and molecules high in the atmosphere. Oxygen and nitrogen absorb the energy, then release it as shimmering light. Greens, reds, purples, and blues can ripple across the sky like curtains drawn by invisible hands. The display may look soft, but it is connected to powerful space weather. Strong solar storms can disturb satellites, radio signals, and power systems. Auroras are therefore both beauty and warning. They show that Earth is not isolated from the sun. Our planet sits inside a changing stream of solar material, protected by magnetism, yet still touched by the star that gives us light. The Van Allen belts trap charged particles around Earth. Surrounding our planet are regions where energetic particles are caught by Earth's magnetic field. These zones were discovered in the early space age, when instruments revealed radiation circling above us in great belts. Many of the particles come from the solar wind, while others are produced when cosmic rays strike the atmosphere. Once trapped, they spiral along magnetic field lines and bounce between northern and southern regions. For spacecraft, this environment matters greatly. Electronics can be damaged, and astronauts must limit exposure during certain missions. Yet the belts are also part of Earth's defense system, shaped by the same magnetic shield that helps protect the atmosphere from direct solar assault. They are invisible from the ground, but they form a vast, restless region around the planet. Earth is not merely sitting in space. It is wrapped in moving radiation and magnetic structure. Satellites can fall from orbit because thin air still exists. Orbit may seem like a perfect vacuum, but near Earth, it is not completely empty. Even hundreds of miles above the surface, traces of atmosphere remain. A satellite moving through that thin gas feels a tiny amount of drag. At first, the effect is almost unnoticeable. Over time, it steals orbital energy, causing the path to shrink. The satellite sinks lower, where the air is thicker, and drag increases further. Without correction, it eventually re-enters the atmosphere and burns, breaks apart, or falls in controlled fragments. Solar activity can make this process stronger by heating and expanding the upper atmosphere. This is why engineers track orbits carefully and sometimes use thrusters to boost spacecraft higher. Falling from orbit is not like dropping from a shelf. It is a slow surrender to the last wisps of Earth's air. Stars are born inside cold clouds of gas and dust. The birthplaces of stars are not fiery at first. They begin in dark, cold molecular clouds, where gas and dust drift together across vast regions of space. Gravity slowly gathers denser pockets within these clouds. As a pocket collapses, it spins, flattens, and heats at the center. The growing core becomes a protostar, hidden behind dusty material that blocks visible light. Around it, a disk may form, and within that disk, planets can begin to assemble. Eventually, if the core becomes hot and dense enough, hydrogen fusion starts. A new star ignites, and its radiation pushes away some of the surrounding cloud. What began as darkness becomes a source of light. In this way, stars are not simply placed into the universe. They condense out of cold material, awakening from shadow into brilliance. A star's color reveals its temperature. When people imagine heat, they often think of red as hottest and blue as cooler. Stars teach the opposite lesson. A red star is relatively cool on the stellar scale, while a blue star burns at far higher temperatures. The color comes from the star's surface temperature, which shapes the kind of light it gives off most strongly. Cooler stars glow red or orange. Stars, like the sun, shine yellow-white. The hottest stars blaze blue-white and pour out intense ultraviolet radiation. This color is not decoration. It tells astronomers about mass, lifespan, energy output, and even the conditions around nearby planets. With one glance through instruments, a star's shade becomes a clue to its nature. The night sky is therefore not simply sprinkled with lights. It is written in colors that reveal the hidden heat of suns. Blue stars burn hotter and die faster than red stars. A massive blue star can look like a symbol of power, and in many ways it is. Its core burns through fuel at an extraordinary rate, producing intense radiation and strong stellar winds. Because it has so much mass, gravity squeezes the core fiercely, which drives fusion faster. The result is brilliance at a cost. These stars may live only millions of years, a brief life by cosmic standards. Smaller red stars use their fuel slowly and carefully, lasting far longer than the current age of the universe in some cases. The contrast is striking. The brightest stars are often the most short-lived, while the dimmest can endure almost beyond imagination. In space, extravagance burns quickly. A blue star gives the universe a dazzling flare of energy, then races toward transformation, collapse, or explosion. Red dwarfs may shine for trillions of years. Red dwarfs are small, cool stars, but their modest nature gives them an astonishing advantage. They burn fuel so slowly that many could last for trillions of years. That is far longer than the universe has existed so far. Unlike larger stars, some red dwarfs can mix their hydrogen efficiently, allowing them to use a greater share of their fuel. They are also the most common type of star in the galaxy, filling space with faint, long-lived points of light. Because they are dim, planets must orbit close to receive enough warmth, which can create challenges such as tidal locking and stellar flares. Even so, their longevity makes them fascinating places to study. Around these patient stars, time stretches into futures our sun will never see. Red dwarfs are the slow lanterns of the cosmos. Some stars pulse like cosmic hearts in steady rhythms. Not every star shines with perfect steadiness. Some expand and contract in repeating cycles, growing brighter and dimmer in patterns that astronomers can measure. These pulsating stars change because forces inside them fall in and out of balance. Pressure pushes outward, gravity pulls inward, and their outer layers respond like breathing envelopes of gas. Certain kinds, such as Cepheid variable stars, are especially valuable because their rhythm reveals their true brightness. By comparing true brightness with how bright they appear from Earth, astronomers can measure enormous distances across space. That means a pulsing star can become a cosmic measuring tool. Its light rises and falls, and that pattern helps map the universe. What sounds like a simple flicker is actually a signal, carrying information about size, distance, and the hidden structure of the heavens. Neutron stars can spin hundreds of times each second. When a massive star collapses, its core can shrink into an incredibly compact neutron star. If the original star was rotating, the collapse makes it spin much faster, just as a skater spins faster when pulling in their arms. The result can be almost unbelievable. Some neutron stars rotate hundreds of times per second, packing more mass than the Sun into a sphere only about the size of a city. Their surfaces are governed by gravity far stronger than anything on Earth. Their interiors contain matter squeezed into states we cannot recreate in ordinary laboratories. A single rotation happens faster than a blink, yet the object itself is heavier than a star. These remnants show what happens when nature compresses matter to extremes. A dead star can become one of the fastest, densest clocks in the universe. A teaspoon of neutron star matter would outweigh a mountain. Density is easy to underestimate because everyday matter is mostly empty space at the atomic level. In a neutron star, that emptiness has been crushed away to an extraordinary degree. Protons and electrons are forced together, forming neutrons packed incredibly tightly. The result is matter so dense that a tiny amount would have a mass beyond anything familiar. A spoonful would weigh billions of tons if it could somehow be brought to Earth, although in reality it could not remain stable outside the star's crushing gravity. This is matter at the edge of comprehension. It is not merely heavy like lead or stone. It belongs to a state created by stellar collapse, where gravity has overwhelmed ordinary atomic structure. Neutron stars remind us that the universe contains forms of matter more extreme than imagination can comfortably hold. Pulsars sweep beams of radiation like lighthouse signals. A pulsar is a rotating neutron star with beams of radiation shooting from its magnetic poles. If one of those beams crosses Earth, telescopes detect a regular pulse, sometimes with astonishing precision. The star itself is not turning on and off. It is spinning, and its beam sweeps across space again and again. Some pulsars are so reliable that they rival atomic clocks over long periods. Their signals allow scientists to test gravity, study interstellar space, and search for tiny disturbances caused by gravitational waves. The first pulsar discovery was so strange that researchers briefly wondered if the pulses might be artificial. Nature was the answer, but the truth was no less remarkable. A collapsed star, city-sized and wildly dense, can send a rhythm across the galaxy that arrives at Earth like a heartbeat from deep space. Magnetars have magnetic fields beyond ordinary imagination. Some neutron stars possess magnetic fields so powerful that they become a special class called magnetars. Their magnetism is trillions of times stronger than anything most people encounter on Earth. At close range, such a field would distort atoms and disrupt ordinary matter. Magnetars can produce sudden flares of high-energy radiation when stresses in their crust and magnetic field release enormous amounts of energy. A flare from one within our galaxy has affected Earth's upper atmosphere, even across vast distance. These objects are rare, brief-lived, and intensely strange. They are not large by astronomical standards, yet their magnetic influence is almost terrifying in scale. A magnetar shows that after a star dies, it may leave behind not only dense matter and strong gravity, but a magnetic engine powerful enough to announce itself across thousands of light years. Supernovas can outshine entire galaxies for a short time. When certain stars die, they do not fade gently. A massive star can collapse and rebound in a catastrophic explosion, while a white dwarf in another system can detonate after gaining too much mass. In both cases, the release of energy can be immense. For days or weeks, a supernova may shine brighter than the combined light of billions of ordinary stars in its galaxy. These explosions are destructive, but they are also creative. They scatter newly forged elements into space, stir nearby gas clouds, and sometimes trigger fresh rounds of star formation. The calcium in bones and iron in blood are connected to such cosmic violence. A supernova is therefore not only an ending. It is a redistribution of ingredients, a brilliant announcement that one star's death can help prepare the material for future worlds. Heavy elements are scattered through space by dying stars. A star spends its life making new elements in layers, like a furnace with different chambers. Near the end, the largest stars contain shells of carbon, oxygen, silicon, and heavier materials surrounding a dense core. When collapse begins, the star can explode with breathtaking force. The blast throws those enriched layers outward into space, where they mix with gas clouds between stars. Over time, that material becomes part of new star systems. This is how the universe recycles itself. The atoms in rocks, oceans, air, and living cells are not freshly invented on one planet. They are inherited from earlier generations of stars. Death becomes distribution. A stellar ending can seed a future world with chemistry complex enough for mountains, seas, and life. Every metal vein in Earth carries a memory of ancient cosmic fire. Gold may form when neutron stars collide. For a long time, scientists wondered where the universe made many of its heaviest elements. Ordinary stellar fusion cannot easily build them all. Then astronomers observed the aftermath of two neutron stars spiraling together and merging. The event released gravitational waves, light, and a cloud of neutron-rich debris. In that extreme environment, atomic nuclei could rapidly capture neutrons and build heavy elements, including gold, platinum, and others. The glow from such a collision is called a kilonova. It is not only a violent merger between dead stars. It is a cosmic forge that can create treasure. The gold in a ring or a tiny fleck in stone may have begun in one of these rare collisions, long before Earth existed. Something precious on your hand may be the cooled remnant of a star crash. White dwarfs are the glowing cores of dead stars. When a star like the Sun reaches the end of its active life, it sheds its outer layers into space. What remains is a dense, hot core called a white dwarf. It no longer produces energy through ordinary fusion, but it can shine for billions of years from leftover heat. A white dwarf can contain a mass comparable to the Sun inside a sphere roughly the size of Earth. That makes it incredibly dense, though not as extreme as a neutron star. Slowly, it cools and fades, moving toward a darker future. Around some white dwarfs, astronomers have found traces of broken planets and rocky debris. This means even after a star's gentle death, pieces of its old system may still orbit nearby. A white dwarf is not just an ember. It is the compact memory of a vanished sun. Some dead stars can explode after stealing gas from companions. In a close binary system, one star can survive as a white dwarf while another continues to evolve beside it. If the pair orbit near enough, the dense remnant can pull gas away from its companion. That stolen material spirals inward and piles onto the white dwarf. If enough mass gathers, pressure and temperature can rise until runaway nuclear reactions ignite. The result can be a type of supernova so bright and consistent that astronomers use it to measure cosmic distances. These explosions helped reveal that the expansion of the universe is accelerating. The story is strangely dramatic. A star that seemed finished can return in one final flash after feeding from its neighbor. What looks like a quiet remnant can become a cosmic marker, bright enough to help map the universe. Betelgeuse is a red supergiant nearing the end of life. Betelgeuse is one of the most famous stars in Orion, and it is enormous. If placed at the center of our solar system, its outer layers could reach beyond the orbit of Mars or even farther, depending on how its shifting surface is measured. It is swollen, cool by stellar standards, and unstable. Its brightness changes as its outer layers pulse, convect, and release material into space. One day, Betelgeuse will explode as a supernova. That will not harm Earth because it is far away, but it could become spectacularly bright in our sky. Astronomers do not know exactly when this will happen. It could be soon in cosmic terms, or far beyond any human lifetime. Watching Betelgeuse is like watching an old giant breathe, knowing its final act is waiting somewhere ahead. The sun will become a red giant one day. Our star is stable now, but it will not remain this way forever. As hydrogen in its core becomes depleted, the balance between gravity and outward pressure will change. The core will contract and heat, while the outer layers expand enormously. The sun will swell into a red giant, becoming much larger and brighter than it is today. The inner planets will face extreme conditions, and Earth's surface will no longer be a place for oceans or familiar life. This future lies billions of years away, but it is written into the life cycle of stars like ours. The sun is not a permanent lamp. It is a changing star with a beginning, a middle, and an ending. Its future transformation reminds us that even the source of daytime is part of cosmic evolution. Our sun will eventually fade into a white dwarf. After its red giant phase, the sun will shed its outer layers into space. Those layers may form a glowing cloud, briefly illuminated by the exposed core. What remains will be a small, dense, stellar remnant. It will no longer warm the solar system as it once did. Instead, it will cool slowly over immense periods, fading from brilliant white to dimmer shades as its stored heat escapes. The planets, if any remain in stable orbits, will circle a quieter relic. This is not a sudden disappearance. It is a long decline measured across time spans far beyond human history. The final sun will be Earth-sized, dense, and cooling. The star that once powered forests, winds, storms, and oceans will become a small ember, carrying the memory of all the light it gave. Star clusters can hold thousands of stars born together. Stars often form in families rather than alone. A single giant cloud of gas and dust can collapse into many newborn stars at once, creating a cluster. Some clusters are loose and young, with bright blue stars still burning fiercely. Others are ancient globular clusters, packed with hundreds of thousands of stars in dense spherical swarms around galaxies. In young clusters, astronomers can study stars that formed from the same material but have different masses. This makes them natural laboratories for understanding stellar lifetimes. Over time, gravity and galactic tides can pull clusters apart, spreading siblings through space. Our own sun may have been born in such a group before drifting away. A star cluster is a cosmic nursery, a gathered generation of suns beginning their lives from the same cold cloud. Nebulas glow because nearby stars excite their gases. Some of the most beautiful objects in space are vast clouds of gas lit from within or nearby. When hot young stars pour out ultraviolet radiation, that energy strikes atoms in the surrounding nebula. The atoms absorb the energy, then release it as light at specific colors. Hydrogen often glows red or pink. Oxygen can shine greenish or blue. The result is not painted decoration, but physics made visible. These glowing regions may surround newborn stars, mark places of active star formation, or outline material shed by dying stars. Their shapes are sculpted by radiation, winds, gravity, and sometimes shock waves. A nebula can be both delicate and powerful, a place where gas becomes luminous, and where new stars may still be forming inside denser pockets hidden from ordinary sight. Dark nebulae hide newborn stars behind curtains of dust. Not every cloud in space glows. Some appear as black shapes against brighter backgrounds, blocking starlight behind them. These dark nebulae are filled with cold gas and dust grains. The dust absorbs and scatters visible light, creating silhouettes that can look like holes in the sky. Yet, they are not empty. Inside their densest regions, gravity may be gathering material into protostars. Infrared telescopes can peer through much of the dust and reveal hidden warmth where star formation is underway. These clouds are important because they show the earliest stages of stellar birth before brilliant light breaks free. A dark nebula is not a dead patch of sky. It is a sealed chamber, cold and obscured, where new suns may be forming behind the veil. The Milky Way contains a supermassive black hole at its center. At the heart of our galaxy lies Sagittarius, a star, a compact object with the mass of millions of suns. We cannot see the black hole directly, but we can watch nearby stars whipping around it at extraordinary speeds. Their orbits reveal a huge amount of mass packed into a tiny region. Radio telescopes have even imaged the hot, glowing material around its shadow. Compared with some giant black holes in other galaxies, ours is fairly calm at present. It is not devouring enough material to blaze as a quasar. Still, it anchors the central region of the Milky Way and offers scientists a nearby laboratory for strong gravity. Our galaxy has a hidden heart. Around it, stars move like dancers around an invisible weight. Black holes are not cosmic vacuum cleaners. A black hole does not suck in everything around it simply because it exists. From far enough away, its gravity behaves like the gravity of any other object with the same mass. If the Sun was somehow replaced by a black hole of equal mass, Earth would not instantly fall in. It would keep orbiting, although life would lose sunlight. The danger comes from getting too close. Near the event horizon, gravity becomes extreme, and paths that once led outward can curve inward forever. Black holes can feed on nearby gas, dust, or unlucky stars, but only material that strays into their reach is captured. This distinction matters because it makes black holes more understandable. They are not magical drains in space. They are regions where mass has been compressed so tightly that escape becomes impossible. Light can orbit a black hole before escaping. Around a black hole, space-time curves so strongly that even light can follow strange paths. At a certain region outside the event horizon, photons can circle the black hole in unstable orbits. This area is sometimes called the photon sphere. A beam of light there is balanced on a knife edge. A tiny disturbance sends it either outward into space or inward toward no return. This effect helps shape the bright rings and shadows seen in black hole images. Light from hot gas near the black hole can bend around it, giving astronomers a view of regions that would otherwise be hidden. The idea feels almost impossible because light usually represents straightness and speed. Near a black hole, even the fastest thing in the universe can be trapped into a curved path. Some black holes are heavier than entire small galaxies. At the centers of many large galaxies sit supermassive black holes, but some grow to truly staggering sizes. They can reach billions of times the mass of the Sun. That means a single invisible object can outweigh all the stars in a small galaxy. These giants likely grew by feeding on gas, merging with other black holes, and living in dense galactic centers where material was plentiful. When actively feeding, the region around them can release more energy than the whole galaxy that hosts them. Their gravity influences nearby stars and gas, and their outflows may help regulate how galaxies evolve. A black hole itself emits no light from within the event horizon, yet its surroundings can become some of the brightest known objects. Darkness, under the right conditions, can power astonishing brilliance. Hawking radiation suggests black holes may slowly evaporate. Classical physics once made black holes seem like one-way traps that could only grow. Then quantum theory changed the story. Stephen Hawking showed that effects near the event horizon imply black holes should emit a tiny amount of radiation. For large black holes, this radiation is unbelievably weak, much colder than the cosmic background around them. But over immense timescales, if a black hole absorbs less energy than it emits, it could gradually lose mass. Very small black holes would evaporate faster. This idea links gravity, quantum physics, and thermodynamics in a deep and unresolved way. No one has directly observed Hawking radiation from an astrophysical black hole, but the prediction reshaped how scientists think about them. It suggests that even the darkest objects may not last forever. Their endings would be slow beyond imagination. Gravitational waves are ripples made by moving space-time. When massive objects accelerate, they can disturb the fabric of space-time itself. The strongest detectable ripples come from extreme events, such as merging black holes or neutron stars. These waves spread outward at the speed of light, stretching and squeezing space by incredibly tiny amounts as they pass. By the time they reach Earth, the change is far smaller than the width of an atom, yet sensitive instruments can measure it. This opened a new way to study the universe. Instead of only collecting light, scientists can now detect vibrations in space-time. It is like gaining a new sense for cosmic events that might otherwise remain hidden. A collision far away can make the universe tremble, and after traveling for ages, that faint tremor can still whisper through instruments on Earth. Scientists first detected gravitational waves from colliding black holes. In 2015, detectors on Earth recorded a signal unlike any seen before. It came from two black holes spiraling together more than 1 billion years ago. As they orbited faster and faster, they released energy as gravitational waves. Then they merged into a single larger black hole, producing a final ringing signal. The detection confirmed a major prediction of Einstein's theory of relativity and began gravitational wave astronomy. Nothing about the event was visible through ordinary telescopes because black holes themselves do not shine. Yet the motion of space-time carried the news across the cosmos. The signal lasted only a fraction of a second in the detectors, but it represented a colossal event. For the first time, humans had not just seen the universe. We had heard its deep structure move. Space-time bends around mass like an invisible cosmic fabric. Gravity is not only a force pulling objects together in the old familiar sense. In Einstein's description, mass and energy shape space-time, and objects follow the curves that result. Earth orbits the Sun because it is moving through curved space-time around the Sun's mass. Light also follows these curves, which is why massive galaxies can bend and magnify the light from objects behind them. This effect is called gravitational lensing. It allows astronomers to study distant galaxies, map hidden matter, and even find planets in certain cases. The image of a fabric is only an analogy, but it helps. Matter tells space-time how to curve, and curved space-time tells matter how to move. The universe is not a rigid stage. It is flexible geometry, shaped by everything within it. Gravity travels at the speed of light. If the sun could vanish instantly, Earth would not feel the gravitational change immediately. The change would travel outward at light speed, reaching us after the same delay as sunlight. This does not happen in reality, but the thought experiment reveals something important. Gravity is not an instantaneous command across space. It is part of the structure of spacetime, and changes in that structure propagate at a finite speed. Gravitational wave detections support this picture, especially when a neutron star merger produced both gravitational waves and light that arrived close together after traveling across cosmic distance. The result showed that gravity and light move at essentially the same speed through space. Even the most fundamental influences in the universe obey a cosmic speed limit. Distance matters, not only for light, but for gravity itself. Time passes slightly faster on satellites than on Earth. A clock in orbit does not tick at exactly the same rate as a clock on the ground. Two effects are involved. Because satellites move quickly, relativity says their clocks should run a little slower. But because they are farther from Earth's gravity, their clocks run slightly faster. For navigation satellites, the gravitational effect is larger, so their clocks gain time compared with clocks on Earth. The difference is tiny each day, but it matters. Without correcting for it, satellite navigation would become inaccurate very quickly. This means relativity is not just an abstract idea for black holes and distant galaxies. It is built into technology people use for maps, travel, shipping, and timing. Every accurate position from a satellite depends on understanding that time itself changes with speed and gravity. The Big Bang was not an explosion into empty space. It is easy to imagine the beginning as a blast happening somewhere in darkness, but that picture is misleading. There was no empty arena waiting for matter to fill it. Space itself was expanding. Every region was once compressed into a hotter, denser state, and then distances began increasing everywhere at once. This means the beginning did not happen at one central point in space. It happened to space. As the universe expanded, it cooled enough for particles, atoms, stars, and galaxies to eventually emerge. The name can make it sound like a firework, but the reality is stranger and deeper. It was the unfolding of the stage on which all later events would happen. Every direction we look carries evidence of that early hot beginning, stretched across the sky like a memory written into the universe itself. Ancient microwave light still fills the entire universe. Long after the first expansion began, the universe was still filled with hot, trapped light. Photons could not travel freely because they kept scattering from charged particles. Then the universe cooled enough for electrons and nuclei to join into atoms. Light was suddenly able to move across space, and that ancient release is still with us today. It has been stretched by cosmic expansion into faint microwave radiation. It comes from every direction, almost perfectly uniform, yet with tiny temperature differences that reveal the seeds of later structure. Those slight variations help scientists understand how galaxies eventually formed. This glow is not coming from stars. It is older than stars. It is the afterglow of a time when the universe first became clear, a background whisper from the young cosmos that still surrounds every world, every galaxy, and every observer. The universe became transparent after atoms first formed. For its first long chapter, the cosmos was like a glowing fog. Free electrons filled space and scattered light again and again, preventing photons from traveling far. Then expansion cooled everything enough for electrons to settle around atomic nuclei. Hydrogen and helium atoms formed, and the fog lifted. Light could finally stream across the universe without constantly being blocked. This moment happened hundreds of thousands of years after the beginning, and it changed everything. It gave us the oldest light we can directly observe today. Before it, the universe is hidden from ordinary light-based astronomy. After it, radiation could travel freely and carry information across cosmic time. The formation of atoms was not just a chemistry event. It was the moment the universe became visible to itself, opening the first clear window through which its earliest structure could eventually be studied. Galaxies grow by merging with smaller galaxies. A galaxy is not born complete and then left unchanged. It grows through gravity, collecting gas, stars, dark matter, and sometimes entire smaller galaxies. When a large galaxy captures a dwarf galaxy, the smaller system can be stretched into streams, its stars scattered into the halo, and its gas folded into future star formation. These mergers can look violent on grand scales, but individual stars rarely collide because the distances between them are enormous. Instead, the shapes of galaxies are transformed by gravity. Spirals can be disturbed. Ellipticals can be built from repeated encounters. The Milky Way carries evidence of past meals in the motions and chemistry of its stars. A galaxy is therefore more like an unfolding history than a fixed object. Its present shape is a record of everything it has gathered, disturbed, and absorbed. Andromeda is moving toward the Milky Way. Far across intergalactic space, our nearest large galactic neighbor is approaching. Andromeda and the Milky Way are drawn together by mutual gravity, and in several billion years they are expected to begin a vast merger. The word collision sounds alarming, but stars are so widely spaced that direct impacts will be extremely rare. The real drama will be gravitational. Both galaxies will stretch, twist, and fling streams of stars into new orbits. Gas clouds may compress and spark new star formation. Over time, the two great spirals may settle into a larger, more rounded galaxy. From Earth, if anyone were here to watch, the night sky would change beyond recognition. Andromeda is not merely a distant smudge in binoculars. It is the future partner of our galaxy, already approaching through the dark with majestic inevitability. Future astronomers may see far fewer galaxies. The universe is expanding, and that expansion is accelerating on the largest scales. Over immense stretches of time, galaxies beyond our local gravitational group will appear to move away faster and faster. Their light will become stretched, dimmed, and eventually impossible to detect. A civilization in the far future might look into the night and see a much emptier universe than we do. Nearby, merged galaxies would remain, but the wider cosmic web could fade beyond reach. This is a haunting idea, because our age may be unusually rich for astronomy. We can still observe distant galaxies, ancient light, and evidence of expansion. The universe is offering clues now that may not be available forever. Our telescopes are not only looking outward, they are looking during a cosmic window when the broader universe can still be seen. Cosmic expansion stretches old light into redder wavelengths. As space expands, it carries light along with it. A photon traveling for billions of years has its wavelength stretched by the growing universe. Longer wavelengths correspond to redder light, and for the most distant objects, visible light can be stretched into infrared or even microwave radiation. This effect is called cosmological redshift, and it is one of the key signs that the universe is expanding. It also means distant galaxies are not just far away in space. Their light has been changed by the history of space itself. Astronomers measure this stretching to estimate distances and look back into earlier eras. The farther a galaxy is, the more its light has usually been stretched. In that reddening, we read the expansion of the cosmos. Every old photon carries a record of the universe growing while it traveled. Dark energy appears to be speeding up cosmic expansion. For much of scientific history, many expected gravity to slow the expansion of the universe over time. Galaxies pull on one another, and matter attracts matter. Then, observations of distant supernovas revealed something surprising. The expansion was not slowing as expected. It appeared to be accelerating. To describe whatever is driving that acceleration, scientists use the name dark energy. It is not dark because it is shadowy, but because its nature remains unknown. It may be a property of space itself, or it may point toward physics not yet understood. Whatever it is, it dominates the large-scale fate of the cosmos. Its influence grows important across the vast spaces between galaxy clusters. The mystery is immense. The universe is not merely expanding. Something woven into its fabric seems to be urging that expansion onward. Dark matter shapes galaxies without giving off light. Galaxies rotate in ways that visible matter alone cannot explain. Stars far from galactic centers move too quickly to be held by the gravity of observed stars and gas unless extra mass is present. This unseen mass is called dark matter. It does not shine, reflect, or absorb light in the usual way, but its gravity affects everything around it. It forms vast halos around galaxies and helps guide the growth of cosmic structure. Without it, galaxies like the Milky Way might not have formed in the same way. Scientists have not yet identified the particle or substance responsible, but the gravitational evidence appears again and again, from galaxy rotation to gravitational lensing and the distribution of galaxies. Clusters. Dark matter is invisible, yet it acts like scaffolding. It helps build the luminous universe while remaining hidden from view. The cosmic web links galaxies in vast invisible threads. On the largest scales, galaxies are not scattered randomly. They gather along filaments, sheets, and knots, separated by huge empty regions. This structure is called the cosmic web. Dark matter provides much of the gravitational framework, while gas and galaxies trace its outlines. At the densest intersections, galaxy clusters form. Along the threads, matter flows and gathers over billions of years. Between them lie enormous voids with far fewer galaxies. Computer simulations show that tiny early density differences could grow into this vast pattern through gravity. When astronomers map millions of galaxies, the universe begins to resemble a great network rather than a smooth spread of lights. The cosmic web is one of the grandest structures known. It means every galaxy belongs to a larger architecture, connected across distances so huge they challenge even imagination. Some galaxies are shaped like spirals, others like glowing clouds. Galaxies come in many forms, and each shape tells a story. Spiral galaxies have rotating disks, arms rich with gas and young stars, and central bulges filled with older populations. The Milky Way is one of these, with our Sun located far from the center in a broad stellar disk. Other galaxies appear irregular, without a neat shape, often because gravity from neighbors has disturbed them. Some look like glowing clouds of stars, soft and rounded, with little obvious structure. Shape can reveal motion, age, gas content, and history. A spiral may still be making stars in its arms. An irregular galaxy may be recovering from an encounter. A smooth cloud may be the result of ancient mergers. Galaxies are not merely islands of light. Their forms are biographies written by gravity. Elliptical galaxies can contain ancient stars and little new gas. Elliptical galaxies often appear smooth, rounded, and golden compared with bright blue star-forming spirals. Many contain mostly older stars and relatively little cold gas. Without much gas, they cannot easily create large numbers of new stars. Their calm appearance can hide a violent past. Some may have formed through mergers that stirred stellar orbits and used up or expelled gas. Others sit at the centers of galaxy clusters, where they have grown huge by absorbing smaller neighbors. The stars inside move in many directions rather than circling neatly in a flat disk. To the eye, such galaxies may look simple. To astronomers, they are fossils of cosmic history. Their old stellar populations preserve clues about early star formation, past collisions, and the long process by which galaxies age into quieter forms. Quasars are powered by hungry, supermassive black holes. A quasar can shine so brightly that it is visible across billions of light-years. The light does not come from inside a black hole, since nothing escapes from within the event horizon. It comes from material swirling around a supermassive black hole before falling in. Gas in the accretion disk becomes extremely hot as friction, compression, and magnetic forces release energy. The region can outshine the galaxy around it. Some quasars also launch powerful jets that race outward at nearly light speed. They were more common in the earlier universe, when galaxies contained more available gas to feed their central black holes. A quasar is therefore a sign of appetite on a cosmic scale. It is a galaxy's central darkness surrounded by one of the brightest engines nature can produce. Some galaxies blast jets longer than the galaxies themselves. In certain active galaxies, material near a central supermassive black hole is organized by magnetic fields and launched outward in narrow jets. These jets can extend far beyond the visible galaxy, crossing hundreds of thousands or even millions of light years. They are made of energetic particles moving at incredible speeds, often producing radio waves that telescopes can detect. The black hole does not shoot material from inside itself. The jets come from the turbulent region around it, where gas, rotation, and magnetic fields combine in extreme conditions. These outflows can heat surrounding gas and affect whether new stars form. A galaxy may look like a quiet collection of stars in visible light, yet in radio waves it can reveal enormous structures reaching into intergalactic space. Its hidden engine can influence regions far larger than the galaxy's starlit body. The earliest galaxies formed surprisingly soon after the Big Bang. As telescopes have grown more powerful, they have found galaxies from earlier and earlier cosmic times. Some appear when the universe was only a small fraction of its current age. This challenges scientists to understand how stars, gas, and dark matter gathered so quickly into organized systems. The first galaxies were likely smaller and more chaotic than many modern galaxies, with intense star formation and fewer heavy elements. Their light has been stretched into infrared wavelengths by cosmic expansion, which is why infrared telescopes are so important for studying them. These ancient galaxies are not nearby objects with ordinary histories. They are messages from the universe's youth. Seeing them helps astronomers investigate how the first star cities formed out of darkness and how their radiation and chemistry changed the cosmos around them. Galaxy clusters are the largest structures held together by gravity. A galaxy cluster can contain hundreds or thousands of galaxies bound together in one immense system. Between those galaxies lies hot gas that shines in X-rays, and around them is a vast amount of dark matter. The galaxies are only the most visible pieces. The total cluster is a deep gravitational well, shaping the motion of everything inside it. Clusters can bend light from more distant objects, creating arcs and magnified images through gravitational lensing. They also grow by merging with other clusters, producing collisions so large that they reveal dark matter separating from ordinary gas. On scales beyond clusters, cosmic expansion can overcome local gravity, but inside a cluster, gravity still wins. These structures are cosmic cities of galaxies, bound together across millions of light years by shared mass and history. Empty cosmic voids can stretch across hundreds of millions of light-years. Between the filaments and clusters of the cosmic web lie enormous regions with far fewer galaxies. These are cosmic voids. They are not completely empty, but compared with crowded clusters, they are astonishingly sparse. A void can be so large that light takes hundreds of millions of years to cross it. Their existence helps reveal how structure formed. Gravity pulled matter toward denser regions, leaving underdense regions increasingly empty. Over time, voids expanded relative to the web around them. If a galaxy lives inside one, its night sky might have fewer bright neighboring galaxies than ours does. Voids are important because they show that the universe has texture on the largest scales. It is not evenly filled. It is a landscape of walls, threads, knots, and great open regions where matter is thinly scattered. The observable universe is not the whole universe. We can only see regions whose light has had time to reach us since the beginning of cosmic expansion. That visible region is called the observable universe. It is enormous, but it is not necessarily everything that exists. Beyond the cosmic horizon, there may be more galaxies, more stars, more dark matter, and more structure whose light has not reached us and may never do so. The boundary is not a wall. It is a limit set by time, distance, and the expansion of space. Observers in distant galaxies would have their own observable universes, centered on themselves, overlapping with ours in some regions and extending beyond it in others. This idea changes the meaning of the word universe in everyday speech. What we can observe may be only one visible portion of a far greater whole. Space may be infinite beyond our cosmic horizon. Measurements suggest that the universe is very close to flat on large scales, and one possibility is that space continues without end. If so, beyond the farthest light we can ever receive, there may be more regions much like our own, extending onward without a final boundary. Another possibility is that space is finite, but so vast and gently curved that we cannot detect its overall shape. Both possibilities stretch intuition. An infinite universe would mean no edge, no outside, and no final wall. A finite but unbounded universe would also avoid an edge, much as the surface of Earth has no border despite having a limited area. Either way, the horizon we see is not the end of existence. It is the end of our view, and beyond it may lie distances the mind can name but not truly picture. The universe has no known center or edge. From Earth, distant galaxies seem to be receding in every direction, but that does not place us at the center. In an expanding universe, every observer sees other distant galaxies moving away on large scales. The expansion belongs to space itself, not to galaxies flying outward from a single middle point. The surface of an inflating balloon gives a useful picture. Points on the surface all move farther apart, yet there is no center on the surface itself. The real universe is more complex, but the lesson remains. The Big Bang happened everywhere, not at one location in space. No edge has been found, and no central point is known. This is one of the most humbling ideas in cosmology. We are not sitting at the middle of the cosmos. We are inside an expanding whole. Exoplanets have been found around thousands of distant stars. For most of human history, planets beyond our solar system were only imagined. Now we know they are everywhere. Astronomers have discovered thousands of confirmed worlds orbiting other stars, and many more candidates are waiting to be studied. Some were found because they tugged their stars slightly back and forth. Others revealed themselves by passing in front of their stars and dimming the light by a tiny amount. These methods are delicate, yet they have opened an entire galaxy of possibilities. We have found worlds larger than Jupiter, worlds smaller than Neptune, rocky planets, scorched planets, frozen planets, and planets in systems unlike our own. The night sky is no longer just a field of stars. It is filled with suns that may carry hidden families of worlds around them. Some exoplanets orbit two suns at once. Science fiction pictured worlds with double sunsets long before telescopes confirmed that such places exist. In some star systems, two stars orbit each other closely, and a planet circles around both of them. These are called circumbinary planets. Their skies would be governed by changing light, shifting shadows, and seasons more complicated than anything on Earth. The planet's path must be stable enough to avoid being flung away by the tug of two stars, which makes these systems especially fascinating. Some have been discovered by watching starlight dip in repeating patterns as planets cross in front of their paired suns. The idea is beautiful because it feels both alien and understandable. A horizon could hold two dawns, two noons, and two fading lights at day's end, all guided by gravity's careful choreography. Hot Jupiters race around their stars in only days. Some giant planets orbit so close to their stars that their years last only a few Earth days. These worlds are called hot Jupiters because they resemble Jupiter in size, but they live in blistering heat. Their atmospheres can swell under intense radiation, and some are slowly losing gas into space. They were among the first exoplanets discovered because their gravity tugs strongly on their stars, and their large disks block noticeable starlight during transits. Their existence surprised scientists. Giant planets were expected to form farther from stars, where ices could help build large cores. Hot Jupiters suggest that planets can migrate dramatically after forming, shifting inward through interactions with disks or other planets. They reveal that solar systems are not always neat clockwork arrangements. Some are restless, rearranged, and extreme. Some planets are hotter than certain stars. A planet can become so intensely heated by its star that its day side reaches temperatures beyond those of the coolest stars. These ultra-hot worlds often orbit very close to bright, powerful suns, receiving relentless radiation. Their atmospheres can become so hot that molecules split apart, metals vaporize, and winds carry material from day to night. On the night side, atoms and molecules may recombine, releasing energy in strange cycles of atmospheric chemistry. These planets blur the familiar boundary between worlds and stars. They are not massive enough to sustain fusion like true stars, yet their surfaces and skies can glow with extraordinary heat. They show that the word planet does not always mean cool rock, pale cloud, or distant ice. Some planets are furnaces, forced into brilliance by the stars they nearly touch. One distant world may rain molten glass sideways. One famous exoplanet is a deep blue giant with weather that sounds almost impossible. It orbits close to its star, where temperatures are fierce and winds may race at thousands of miles per hour. Its blue color likely comes not from oceans, but from tiny silicate particles in the atmosphere. Silicates are the building blocks of glass. Under those conditions, they may condense into droplets and fall through the sky, while violent winds drive them sideways. The image is astonishing, but it is grounded in atmospheric science. Weather is not limited to water vapor and clouds like ours. On other worlds, rain can be made of minerals, metals, or exotic chemistry shaped by heat and pressure. This planet reminds us that nature does not design skies for comfort. It designs them from available ingredients. Carbon-rich planets could hide vast interiors of diamond. Planets form from the chemistry surrounding their young stars. If a system contains more carbon relative to oxygen than ours does, some rocky planets may develop very different interiors. Under high pressure, carbon can form diamond. This does not mean a sparkling gemstone world covered in jewels. The reality would be darker, heavier, and stranger. Deep below the surface, carbon-rich layers could be compressed into vast crystalline structures. Such planets might have unusual geology, different volcanic chemistry, and interiors unlike Earth's silicate mantle. Scientists have proposed candidates, although proving their composition remains difficult. The possibility still changes how we imagine worlds. Earth is built from one particular recipe. Elsewhere, the ingredients may vary enough to create planets where ordinary rock gives way to carbon structures formed under unimaginable pressure, hidden far beneath an alien surface. Ocean planets may be covered by seas thousands of miles deep. Some distant worlds may contain far more water than Earth. Instead of continents and shallow ocean basins, they could be wrapped in global seas extending to incredible depths. At the surface, there might be waves, clouds, and storms. Far below, pressure would become so extreme that water could form exotic high-pressure ice, even while temperatures remain warm enough for liquid layers above. This kind of ice is not like frozen ponds on Earth. It is a dense form created by crushing weight. The deepest ocean might be separated from the rocky core, which could affect chemistry and habitability. Still, such worlds are fascinating because they expand the idea of what a planet can be. Earth has oceans resting on rock. These planets may be oceans first, with rock hidden far below like a distant memory. Super-Earths are common, but absent from our solar system. Many exoplanet systems contain worlds larger than Earth but smaller than Neptune. Astronomers call them super-Earths when they are likely rocky or partly rocky, although the name does not mean they are better than Earth. Strangely, our own solar system has none. We move from small rocky planets to giant worlds without anything in between. This absence makes our system feel less typical than once assumed. Super-Earths can vary widely. Some may have thick atmospheres. Some may be ocean-rich. Others may be rocky and hot. Their gravity would be stronger than Earth's, and their geology could follow different patterns. Because they are common around other stars, they may hold important clues about how planets form and migrate. The universe seems to build many worlds in a size range our neighborhood somehow skipped. Rogue planets may outnumber stars in the galaxy. There may be countless planets drifting through space without orbiting any star. Some were probably born in planetary systems and later thrown out by gravitational encounters. Others may have formed alone from small collapsing clouds. Since they do not shine by reflected starlight in the usual way, they are difficult to detect. Astronomers find some through gravitational microlensing, when a wandering object briefly magnifies the light of a more distant star. These worlds could be frozen on the outside, but the largest might retain internal heat for long periods. A few might even hide subsurface oceans beneath thick ice. If rogue planets are as common as some estimates suggest, the galaxy is not only a place of stars and solar systems. It is also filled with dark travelers moving between them, unseen and unclaimed. Some planets could orbit inside the habitable zones of red dwarfs. Red dwarfs are small, long-lived stars, and many have planets. Because they are dim, their habitable zones sit close in, where a planet could receive enough warmth for liquid water under the right conditions. This makes them exciting targets in the search for life. But close orbits bring complications. A planet may become tidally locked, with one side always facing the star. Red dwarfs can also produce powerful flares that may strip atmospheres or bathe surfaces in radiation. Even so, An atmosphere or ocean could move heat around, and magnetic fields or chemistry might offer protection. These systems are worth studying because red dwarfs are so abundant. If even a fraction of their planets remain habitable, the galaxy could contain many small worlds circling faint red suns, waiting in patient starlight. The James Webb Space Telescope unfolded like origami in space. Webb was too large to launch in its final shape, so engineers designed it to fold inside a rocket. After reaching space, it performed a careful sequence of deployments. Its sunshield stretched open in layers, each thinner than a human hair compared with its broad size. Its golden mirror unfolded from segmented pieces into a single observing surface. Every step had to work with extraordinary precision, far from Earth. The telescope then traveled to a stable observing region where it could stay cold enough to detect infrared light. Webb is remarkable not only because of what it sees, but because of how it became itself after launch. It was a machine packed like a folded promise, then opened in space into one of the most powerful eyes humanity has ever built. Webb can study starlight filtered through alien atmospheres. When a planet passes in front of its star, a tiny portion of starlight travels through the planet's atmosphere before reaching us. Molecules in that atmosphere absorb specific colors of light. By studying those missing colors, Webb can identify gases such as water vapor, carbon dioxide, methane, and other compounds. This technique is called transmission spectroscopy, and it lets scientists investigate worlds that are far too distant to visit. The measurements are delicate because the signal is small, often buried inside the bright glare of the star. Yet, with enough observations, an atmosphere begins to reveal itself. We cannot stand on these planets, feel their air, or watch their clouds directly. Still, their skies can leave fingerprints in light, and those fingerprints can cross space to tell us what they are made of. Hubble revealed galaxies where darkness once seemed empty. In the 1990s, astronomers pointed Hubble at a tiny patch of sky that looked almost blank. The telescope stared for days, collecting faint light. The result was astonishing. That dark-looking region was filled with galaxies, each containing billions of stars. Later, deep-field images reached even farther, revealing galaxies from earlier cosmic times. These observations changed the emotional scale of the universe. A speck of apparent emptiness became a window into thousands of star systems and billions of years of history. Hubble showed that darkness in the sky often means our eyes are not sensitive enough. The universe is richer than casual sight suggests. What seems empty may be crowded with ancient light, waiting for a patient telescope to gather it one photon at a time. Radio telescopes can listen to cold hydrogen between stars. Space contains enormous clouds of hydrogen gas, much of it too cold and faint to see with ordinary optical telescopes. But neutral hydrogen emits radio waves at a special wavelength of about 21 centimeters. Radio telescopes can detect this signal and use it to map gas across galaxies. This has revealed spiral arms, rotating disks, tidal streams, and hidden structures extending far beyond visible starlight. Hydrogen is the raw material from which stars can form, so tracking it helps astronomers understand galactic growth and future star birth. Radio astronomy also works through dust that blocks visible light. It lets scientists study regions that would otherwise be hidden. In a poetic sense, the coldest gas in space has a voice of its own. Not sound through air, but a radio whisper carrying the shape of galaxies. Space probes have touched the outer atmosphere of the Sun. The Sun seems unreachable, yet a spacecraft has flown through part of its outer atmosphere, called the corona. Parker Solar Probe was built to survive intense heat and radiation, while passing closer to the Sun than any previous mission. Its heat shield protects instruments, as the spacecraft samples particles and magnetic fields near our star. The corona is mysterious because it is far hotter than the visible surface below it. By flying through this region, the probe helps scientists understand solar wind, magnetic activity, and the processes that affect space weather throughout the solar system. This matters for satellites, astronauts, and power systems on Earth. The mission is daring in a very literal way. Humanity built a machine that can skim the atmosphere of a star and return measurements from the edge of fire. Voyager 1 carries human sounds beyond the solar system. Launched in the late 1970s, Voyager 1 traveled past the giant planets and continued outward into interstellar space. Attached to it is a golden record containing greetings, music, natural sounds, and images encoded as information. The record was not meant for any likely recipient soon. Space is vast, and the chance of discovery is extremely small. Yet its meaning is profound. It is a symbolic message from Earth, carrying waves, wind, heartbeats, birdsong, human voices, and music into the dark between stars. Voyager 1 is now far beyond the planets, still sending faint signals back across billions of miles. Its instruments will eventually fall silent, but the craft will keep moving. A small human-made object will drift through the galaxy, bearing traces of the world that launched it. New Horizons revealed Pluto as active, complex, and strange. Before the spacecraft arrived, Pluto was mostly a blur, even to powerful telescopes. The flyby changed that forever. Images revealed mountains of water ice, smooth plains of nitrogen ice, layered hazes, dark equatorial regions, and a bright Hawk-shaped basin. Some surfaces appeared surprisingly young, with few craters, suggesting geological activity. Scientists saw possible ice flow, cellular patterns in frozen plains, and clues to a complex atmosphere escaping slowly into space. Pluto became more than a distant point at the edge of charts. It became a real world with landscapes, weathering, and history. The encounter also reminded us how much can remain hidden until we go and look. A small dwarf planet, long treated as simple and frozen, turned out to be one of the most visually and scientifically surprising places ever visited. Asteroid samples can reveal chemistry older than Earth. Some asteroids preserve material from the earliest solar system, before planets fully formed. When spacecraft collect samples and return them to Earth, scientists can study grains, minerals, and organic compounds with laboratory tools far more powerful than anything flown in space. These samples may contain tiny particles older than the Sun, along with chemistry that records conditions in the solar nebula. They can reveal how water-bearing minerals formed, how carbon-rich compounds were distributed, and how small bodies contributed ingredients to young planets. Unlike meteorites found on the ground, returned samples can be protected from contamination and linked to a known asteroid. Each speck is precious because it carries information from a time before Earth had oceans, continents, or skies. Holding asteroid material is like touching a fragment of the solar system's beginning. Future telescopes may search nearby worlds for signs of life. The next great question is not only whether planets exist, but whether any of them are alive. Future observatories may study rocky worlds around nearby stars with enough precision to search for atmospheric clues. Gases such as oxygen, methane, carbon dioxide, and water vapor can mean many things, so scientists will need to interpret them carefully. A true biosignature would likely come from patterns that are difficult to explain without biology, seen in the context of the planet's star, climate, and geology. This search will be slow, cautious, and extraordinary. We may not find forests, oceans, or creatures directly. We may find a chemical imbalance in distant air. Yet that would be enough to change human history. A faint signal from another atmosphere could suggest that life is not unique to Earth. Outer space keeps proving reality is stranger than imagination. Again and again, the universe has exceeded the stories humans first told about it. We imagined stars as distant lights, then learned they were suns. We imagined planets as rare, then found them everywhere. We pictured space as empty, then discovered fields, radiation, dark matter, and structures larger than anything the eye can grasp. Each generation of instruments reveals something stranger. Moons with hidden oceans, black holes with measurable shadows, galaxies from cosmic dawn, worlds where glass, methane, metal, or ice may shape the weather. The wonder is not that science removes mystery, it deepens it. Every answer opens a wider question, and every distant signal reminds us that nature is more inventive than our first guesses. Outer space is not simply far away. It is the grandest reminder that reality still has surprises left. And so, we come gently back from the stars. Tonight, we wandered through the vastness of outer space, from the first stretching of the universe to ancient light, still drifting through every corner of the cosmos. We followed stars through birth, fire, collapse, and brilliance. We passed black holes where time bends, moons with hidden oceans, planets without suns, and galaxies slowly gathering across the dark. We saw that space is not empty, but alive with motion, radiation, gravity, dust, and distant signals. Even in the silence between worlds, something is always unfolding. And perhaps that is the comfort of it. The universe is vast beyond measure, but it is not still. It is moving, changing, glowing, and becoming in rhythms far older than any worry we carry tonight. So now, let those thoughts drift farther away. Let the planets turn without needing your attention. Let the stars burn softly in the distance. Let the moon continue on its slow path, and let the deep sky hold all the questions for a while. If you enjoyed this journey, you're welcome to like, subscribe, or leave a thought below. It helps other sleepy souls find their way here too. And if you happen to still be awake, there will be another gentle video waiting on the screen, ready to carry you somewhere new. But for now, there is nothing left to do. Let your shoulders soften. Let your breathing slow. Let your thoughts become light and spacious, like starlight fading at the edge of sleep. Sleep well, and good night.